Good morning or good afternoon, everyone. Welcome to our point distribution webinar. We have today a speaker, Alex McDonald from Rochester University, and the title of his talk, "This volume is spanned by cup point configurations in AD." And please do not forget that after the talk, we will have some virtual coffee break or virtual drinks. Okay, so please start.
All right, well, thank you so much for inviting me. So I'm going to be talking about volumes spanned by point configurations in Euclidean space, and the results here are joint with Almira Yala, who's another graduate student of my advisor. Okay, so let's see, is this working? Yeah, okay. Okay, so I'm going to start by giving a quick overview of the Falconer distance problem, which is sort of the motivating problem for one of the early and big motivating problems for the stuff I'm going to be talking about. So for a set E and RD, define the distance set of E to be simply the set of real numbers that you get looking at all the pointwise distances between any pair of points in E. The Falconer distance problem asks, so say E is a compact set, how large must the Hausdorff dimension of E be to ensure that the distance set has positive Lebesgue measure? So it's a subset of the real line. So we're looking at positive one-dimensional Lebesgue measure. Okay, so the original paper by Falconer where he posed this problem has a result. So Falconer proved that if the dimension of E is bigger than d plus 1 over 2, then the distance set has positive measure. And he also gave a class of examples showing that you could have sets whose dimension is less than d over 2, but arbitrarily close to d over 2, such that the distance set has measure 0. So this poses a problem where basically the game is to get better and better thresholds until ultimately the conjectured correct threshold is d over 2. So the conjecture is that any set of dimension bigger than d over 2 has a positive measure distance set. And the game is how close to d over 2 can you get. Okay, so a few results in this direction. So in 1999, Wolf proved that sets in the plane of dimension greater than 4/3 have positive measure distance sets. So Falconer in the plane when d equals 2, that's 3/2. Wolf improved it to 4/3, and Erdogan improved it for higher dimensional case, improved it to d over 2 plus 1/3. So this matches 4/3 when d equals 2. Erdogan proved it for all other d, and this was the best result for a while. So recently, there have been kind of in the last 3 years or so, 3 or 4 years, there have been kind of a bunch of results using the decoupling theorem of Bergon and Demeter by various permutations of 7 or 8 people. So d equals 2, Wolf's 4/3 threshold was improved to 5/4 by Larry Guth, Alex Yosevich, Yuming Wu, and Hong Wang, and so on. So for d equals 3, there's 9/5. When d is greater than or equal to 4, it depends on whether d is even or odd. When d is even, you get d over 2 plus 1/4. When it's odd, you get d over 2 plus 1/4 plus a little bit more. Okay, so I want to talk a little bit about the strategy for approaching these Falconer problems, because it's going to be the strategy we're going to use for point configuration problems as well. So we get our hands on the dimension by looking at these what are called Frostman measures. So if E is a compact set, for any S less than the dimension of E, dimension will always mean Hausdorff dimension throughout this talk. For any S less than the dimension of E, there is a probability measure mu supported on E, which has this decay. So the measure of b sub r of x is a ball of radius r centered at x. Wherever the center is, the measure of b, the measure of the ball of radius r is no more than a constant times r to the s. So throughout, less than with the squiggle means that I'm suppressing a constant. Okay, so you can choose a measure that has this decay property, and this energy integral is finite. And the finiteness of this energy integral lets us, well, actually, I'll just come back to that. It's important for using a lot of the harmonic analysis tools we want to use. Okay, so this measure is called a Frostman probability measure with exponent s. And we're going to study our sets by looking at these measures that they support. Okay, so given such a measure mu, so mu is a Frostman probability measure supported on E, like on the previous slide, we look at a push forward measure nu, where the integral of say, a function f with respect to nu is given by integrating f of the distance between x and y with respect to the product of measure of mu with itself. Okay, and the upshot here is that nu is, by definition, is a probability measure supported on the distance set. So to prove that the distance set has positive measure, it suffices to show that nu is absolutely continuous with respect to Lebesgue measure. Okay, so take some approximate identity and convolve it with nu, and this gives us sort of an approximation to nu. And for any set A and R, this integral on the left is approximating nu of A, right? The nu measure of A. And by Cauchy-Schwarz, it's bounded by, I guess I use vertical bars here to denote Lebesgue measure. So Lebesgue measure of A to the 1/2 times the L2 norm of nu epsilon. And as epsilon goes to 0, the approximation on the left will go to nu of A. So if we can prove uniform L2 bounds on nu epsilon, uniform meaning independent of the parameter epsilon, then it follows that nu is absolutely continuous, and therefore it follows that the distance set has a positive measure. Okay, so this is what I mentioned before, but this strategy generalizes pretty easily. So given a function phi, which takes, let's say, n vectors in Rd and spits out a vector in Rm, you can define a push forward the same way, right? So integrating f of t, t is now a vector in Rm, so integrating f of t with respect to nu is integrating the composition of f with this function phi that we're interested in with respect to nu x1 through nu of xn. You define an approximation in the same way, and if you can get uniform L2 bounds on that approximation, then the image of whatever function you're looking at, phi, has positive measure. So in the Falconer problem, n equals 2, you're taking pairs of vectors, m equals 1, your distance is a real number. But you can kind of apply this framework fairly generally. Okay. So we're going to apply this to point configuration problems. So a k+1 point configuration in Rd is simply an element of Rd producted with itself k+1 times. So throughout, my notation is going to be that superscripts denote the different vectors, the different points in the configuration, and subscripts will denote the real number coordinates of those. So configuration is x superscript 1 through x superscript k or k+1 or however many points you have, and each x superscript I is a vector in d-dimensional space. Okay, so one problem we can talk about is congruence. So we say that two configurations are congruent if you can map one onto the other by rigid motions. So specifically, there exists an orthogonal there exists theta in orthogonal transformation, and there exists z, which we'll view as a translation, such that for all points in the configuration, you can map xi to the corresponding yi using that same theta and z. Right? So we have y equals theta x plus z for all I. Okay, so we say two such configurations are congruent, and you can let delta sub k of E denote the set of congruence classes determined by E. And this gives us a direct generalization of the Falconer problem. We can identify the distance set with the choice of parameter k equals 1, right? Because a distance you can view as encoding a congruence class of 2-point configurations, right? So two-point configurations, two pairs of points determine the same distance if and only if, right? You can translate, choose two of the points, you can translate them together, and then you can rotate to match the other 2 points. So two-point configurations are congruent if and only if they have the same distance. So this suggests a generalization of the Falconer problem. Given a compact set E in RD, how large must the dimension of E be to ensure that delta sub k of E has positive measure? So in order for this to be a good question, we first have to agree on what measure we're taking on delta sub k of E. So when k equals 1, we already decided that we can identify this with the distance set. This is a subset of the real line, so you can take one-dimensional Lebesgue measure. So what about when k is larger? So our choice of measure will depend on whether k is less than or equal to d, or whether k is greater than d. So when k is less than or equal to d, we can do kind of the most obvious thing, which is that it's easy to see that two configurations are congruent if and only if all pairwise distances are the same. So we can identify this space of congruence classes, delta sub k, with a k plus 1 choose 2 dimensional vector, where you're getting your vector by, you have this k plus 1 point configuration. Out of those k plus 1 points, any way you can choose 2 points, you get a distance. So there are k plus 1 choose 2 different distances, and if you just impose an ordering on pairs and take the vector of those distances, you have a subset of Euclidean space with k plus 1 choose 2 dimensional Lebesgue measure. And you can pose this question at the top with respect to that measure. Okay, so as an illustration, this is the case k equals d equals 2. So we have a 3-point configuration in the plane. And suppose that we fix distances corresponding to those bold lines, the lines between x1, x2, and x1, x3. Then you still have this degree of freedom to choose x3, and the last distance could take any value between a minus b if we fix one distance to be a and one distance to be b, the last distance can take any value between the difference in the sum. So this is telling us that if we identify the congruence classes by simply looking at tuples of distances, right? We have like an open set, or we have a positive measure set in our k plus 1 choose 2. We have a set with interior. So with that context, this is a theorem of Greenleaf, Yosevich, Liu, and Paulson from a few years ago. So let k be less than or equal to d, and let E be a compact set. If the dimension of E is bigger than this thing, so d minus a little bit, minus specifically d minus 1 over k plus 1, then delta sub k of E has positive k plus 1 choose 2 dimensional Lebesgue measure. So one thing to point out to connect it to kind of the problem we already understand is that what happens when k equals 1? So when k equals 1, delta sub 1 of E is the distance set. So this is a Falconer problem. When k equals 1, we have this threshold is d plus 1 over 2. So this matches Falconer's original d plus 1 over 2 threshold when k equals 1 and generalizes it for all k. And I guess we can also point out that the threshold gets worse as k gets large. So as k goes to infinity, the threshold goes to d.
I'm sorry, can I interrupt a second, Alex?
Yeah.
Sorry, I missed something. What is the phi in this problem?
So the phi would be the map which takes, so n here would be k plus 1, so we're taking configurations and we're mapping them to m would be k plus 1 choose 2, so we're mapping configurations to these vectors that encode all of the possible distances.
So sorry, but phi is, okay, I see, okay, thank you.
Mm. Okay. Okay, so what happens when k is bigger than d? So when k is bigger than d, the difference kind of qualitatively is that this system of equations becomes overdetermined. So you have a system of equations determined by, you have these k plus 1 choose 2 pairs of points, and you can set them equal to a specified distance. The problem is that I thought I'd written this somewhere. So if you, okay. So we can still identify delta sub kv with the k plus 1 choose 2 tuples of pairwise distances, but the resulting set has measure 0, which you can think it's in some sense a lower dimensional set within our k plus 1 choose 2, right? And the reason is that if we specify some of the values of these t sub ij, if you specify some of the distances, you don't have free range to choose the others. You're forced into finitely many boxes. So to illustrate, we're still in the plane, but now we're going to take one more point than in the previous example. So we already talked about 3 points. What happens if you have 4 points? So if you have 4 points, there are 6 pairwise distances, right? There are 6 pairs at least. Suppose we fix 5 of the pairwise distances as indicated by the bold lines. So we have 1 dashed line that we haven't fixed, and we have 5 fixed distances. As you can kind of see geometrically, there are only 2 possibilities for the distance determined by that last pair, right? You can either have the triangle on the top, or you can, but this would be different if we were in 3 dimensions. So you could have like a hinge, but in 2 dimensions, either the triangle goes up or the triangle goes down, and those 2 distances are kind of the only distances that fit. So once going back to, so this is, in that case, this is a system of 6 equations. Once you fix the value, once you fix the, the right-hand side of 5 of those equations, you've determined the 6th. Okay, so in some sense, the kind of space of congruence classes here isn't really 6-dimensional, it's 5-dimensional. Okay, so how is this handled? So we're going to kind of throughout, we're going to be a little bit, I don't want to get into the technicalities of of dealing with the degenerate cases, but when you're looking at non-degenerate configurations, so in this context, that means you have full affine span, right? These, if you're in 3 dimensions, the points don't line a line or whatever. So if you have full affine span, then 2 non-degenerate configurations are congruent. Again, if and only if you can, map one to the other with the rigid motion. So heuristically, we expect that this should be the dimension of the space of congruence classes, because up to, ignoring degeneracies, you have d times k plus 1 dimensions for your space of all configurations, right? Your points are d-dimensional vectors, and you're looking at a k plus 1 tuple of those. So your space of configurations is d times k plus 1 dimensional. And then you subtract off d plus 1 choose 2, because that's the dimension of the group of isometries that you're sort of taking a quotient by. Okay, so this is what we expect the kind of, so again, you can view this set to be a set of k plus 1 choose 2 tuples, but it's not really full dimensional. This is kind of the right dimension to think of the space of congruence class as having. So with this context, this is a theorem of Konstantino, Josevich, McCurchin, and Pachyanathan, a couple of years after the underdetermined case. So D greater than or equal to 2 and K, I guess I said, well, I guess any K greater than or equal to 1, but what's new here is the K greater than D case, and let M be this dimension I just mentioned. So and I'm not going to go into the details of how they kind of define the configuration space, but you can identify the space of congruences with this m-dimensional space with a natural measure. And under that identification, if the dimension of E is bigger than D minus 1 over K plus 1, then you have a positive measure set of congruence classes. Okay, so those are a couple results that preceded mine. What I did in my paper, and what I'm going to talk about for the rest of my time today, is generalizing this approach to other sort of geometric problems other than distance. So what do we need in order to generalize this? The key ingredient in the proof here is this idea of framing everything in terms of the group action, right? That tells us what the dimension should be, but it also kind of lets us analyze larger kind of overdetermined configurations and reduce matters to the tools that we kind of have for Falconer type problems. So this approach kind of naturally generalizes to other configuration problems when the geometric feature in question can be characterized as like the invariant, as like an invariant quantity of a group action. Okay, so the feature I'm going to look at is volume, and so this is the starting point for the volume problem. So this is a theorem of Greenleaf, Josevich, and Taylor. Given a set E in RD, define the volume set of E, which I guess I'll call script V of E, to be the set of all determinants, determinants of any choice of of D points in your set E. Okay, so this basic kind of geometry tells us this is, like, you can think of this as the volume kind of spanned by D vectors, right? And I guess one comment I'll make is that I'm not going to distinguish between signed and unsigned volumes, because if you have a positive measure's worth of signed volumes, you can, there's only finitely many, then you would have a positive measure worth of the other. So this is the theorem defining the volume set in this way. If E is compact and has dimension greater than D minus 1 plus 1 over D, the volume set has positive Lebesgue measure, and in fact actually has a non-empty interior. Okay, so one observation: if the dimension of E is less than or equal to D minus 1, then E could be contained in a hyperplane and have no hope of having a positive measure worth of volumes determined. So the threshold here is D minus 1 plus 1 over D. You can't improve it by any better than that 1 over D. Beyond that, whether this is sharp or not, I don't know. But that's, so that's the result. Okay, so my work is going to be to generalize this to a K-point configuration type problem, the same way that the congruence problem generalizes the Falconer problem. So this is sort of going to be the base case, the jumping off point to study volumes determined by larger point configurations in Euclidean space. Okay, so again, we have a K-point configuration in RD. So we have K D-dimensional vectors. I'm going to define the volume type of X to be this vector. It looks a little messy, but it's not too bad. So you have K points, and for every way that you can choose D of those points, you determine one volume. So this volume type vector simply encodes all of the K choose D volumes, the same way that we can encode congruence classes by the appropriate number of distances. Okay. So for example, here's a 5-point configuration in R3. The red shaded area is like one of the volumes. So 5 choose 3 is 10. So there's 10 different ways to choose these points. That gives us a 10-dimensional vector describing all of the volumes determined by points, by D points in this configuration. Okay. So given K greater than or equal to D, and E in RD, let V sub K D of E denote the set of volume types determined by configurations of points of E. So yeah, the volume types where all of your, for configurations where all of the points in the configuration come from your set E. And V sub KD will simply denote the space of all volume types. So this kind of sets up a Falconer type problem for configurations of the kinds we've been talking about. So our map phi is going to be the map which takes configurations to their volume types. So it's a map from the space of configurations to this space of volume types VKD, and that's obviously contained in our K choose D dimensional Euclidean space. Okay, so this is again an overdetermined problem, at least for large K. So this is a lower dimensional space, and we have to choose an appropriate measure on it. So this is where the, like with the configuration problem, we're going to kind of look at these volume types in terms of group action, right? So the relevant group here is the special linear group. So if G is in SLD of R, it is clear that G of X and X have the same volume type. So up to some notion of degeneracy, the converse is true as well. So suppose that X configurations with the same volume type, and suppose that X contains a basis. Without loss of generality, let's just say that the first D points are linearly independent. Okay, so this is what I'll mean by non-degenerate in the context of this problem. Non-degenerate means that you don't span a lower dimensional space. So define G to be this matrix. So we think of the X1 through XD and Y1 through YD as the columns of a matrix. Defining it this way guarantees that G of Xi equals Yi for I equals 1 through D. What about the rest of the points? Well, if we write each of the points of X and Y in the respective bases given by the first D points in X and the first D points in Y, then it's not too hard to see that the coordinates have to be the same, just using the fact that the volume types are the same. So you can solve those equations and see that the coordinates are the same, and then this guarantees that all of the points in I are being Xi maps to Yi, being G for all I. Okay, so that means that for every non-degenerate configuration, the property of having the same volume type, that equivalence relation, coincides with the orbits of the group action. Okay, so in particular, that tells us kind of how we can describe the space of volume types. So let EI be the ith coordinate standard basis vector, sorry. For any non-degenerate X, we can map, there's an X tilde of this form with the same volume type. So you can see that T that we're multiplying the Dth entry by. That's simply the volume determined by the first d points of x, right? So the point of what we did here is that you can define your special linear element g with the first, with the basis contained in the configuration. So you take x1 through xd and map them to e1 through ed minus 1, and then whatever scalar multiple of ed you need. And then wherever xd plus 1 through xk go, that's what the z's are going to be. So we can kind of choose this, we can choose these canonical representatives of all of the equivalence classes, namely the elements that look like this, and that lets us identify the space of volume types with this space of parameters. So there's k minus d of these z's, which are each d dimensional. So that's d times k minus d, and then we have one more parameter here in the t. Okay, so we can identify this space of volume types with Euclidean space, or a subset of Euclidean space of dimension d times k minus d plus 1, where again, I'm going to ignore the degenerate configurations, which don't present much of an obstacle. So with this identification, our result is as follows. So let k be greater than or equal to d, greater than or equal to 2, and let m be the dimension I just said, and let E be a compact set in RD. So we have this dimensional threshold again. If dimension of E is greater than d minus 1 over 2k minus d, then the m-dimensional Lebesgue measure of the volume type set is positive. And in fact, you should get that it has non-empty interior. So just as a sanity check, remember I said our starting off point was that theorem of Greenleaf, Yosevich, and Taylor in the k equals d case. If you plug k equals d here, then you get the threshold d minus 1 plus 1 over d, which is what they got. So this is kind of strictly a generalization of that result to larger point configurations. Okay. So, and to remind you of this setup, we take E and we look at this Frostman probability measure supported on E. So it has this ball decay and it has finite energy, finite S-dimensional energy. And we define this push forward where the map phi we're using is the map which takes configurations and assigns volume types. Okay. So we take our convolution with an approximate identity, and our goal is to prove L2 bounds of that approximation to nu independent of epsilon. I wrote nu sub kt, but obviously that should be kd. Okay. So I'm going to start by kind of describing the k equals d case. Which, like I said, is our jumping off point. And then I'll describe how we reduce to that case. So for k equals d, this approximation to nu can be understood in terms of an integral. So we're integrating the d-fold product of mu over the region of vectors where the determinant of the x1 through xd is approximately equal to t. And then we divide by epsilon to take the average. So this is up to constants what our approximation is, and this is the thing we want L2 bounds on. Okay. So we're going to decompose the mu into Littlewood Paley pieces. So let phi be a Schwartz function, which is supported in the range in the annulus with inner radius 1/2 and outer radius 1/4, and equal to 1 in the range from 1 to 2. and let mu j be defined on the Fourier side by mu j hat of xi is equal to mu hat of xi times this phi cutoff. So you can think of this as like a smooth version of a characteristic function. So this is, again, on the Fourier side, we're just taking the Fourier transform of mu and kind of smoothly cutting it off at the scale 2 to the j. So this is, these are the Littlewood-Paley pieces. So when you run the decomposition, oh, did I, yeah, whatever. Okay, so when you decompose all d factors, you get an expression like this. So it's the same integral, and we're now integrating these Littlewood-Paley pieces, mu j1 through mu jd, and summing over all combinations of the indices. And the first thing, or I guess one thing I should mention is that you can really think of all of these indices as being equal to each other, because that's where kind of the mass is. That you can, when say J1 and J2 are very different, you can estimate that away. So so throughout, I'm not gonna kind of go through the technical estimates, but I'm just gonna write this as a sum and a single index J and treat all of the indices as being the same. Okay, so this integral here, if you run one of the integrals, you get a generalized radon transform. So this generalized radon transform is defined by taking the function f and d minus 1 parameters x1 through xd, and integrating so the inputs are x1 through xd minus 1, and then you define this transform by integrating f of xd over the region, over the surface defined by this equation, determinant of x1 through xd equals t. And everything else, don't worry about too much. So we have smooth cutoffs, keeping things compactly supported, and we have a surface measure on that surface. But the point here is that we're defining a transform by taking f and integrating over this surface. Okay, and that's exactly what we have here. So this is like the natural transform that comes up, where we have these functions and we're integrating over this surface, if you kind of do it one variable at a time. Okay, so this tensor product of functions simply means that, I guess I should have written that down, but this is just the function you get by plugging x1 into the first thing, x2 into the second thing, and so on, and multiplying them. So this expression here, when you freeze the sum and look at the integral, if you run one of the integrals, if you run the integral in xd, you get a generalized radon transform of the kind I just defined, and then you have mu1 through mu d minus 1, each in a different variable. So this is an inner product of that generalized radon transform with this tensor product. Okay, so the idea here is that we study the mapping properties of these generalized radon transforms and use them to bound this inner product with Cauchy-Schwarz. Okay, so what mapping properties are we using? First of all, so again, mu sub j is a Littlewood-Paley piece, so it has Fourier support on scale 2 to the j. You can prove that when you apply the generalized radon transform, this also has Fourier support concentrated at scale 2 to the j, in the sense that away from that scale, you can kind of get really good estimates, and that part doesn't matter. So you can think of this kind of morally as being supported on the Fourier side at scale 2 to the j as well. And you also have this Sobolev bound. So RT is a bounded map from L2 to the Sobolev space, the L2 Sobolev space with d minus 1 over 2 derivatives. And this together with Plancherel gives us bounds on this inner product. Right? So this is what we had for our approximation. This is what we wanted to bound. It's equal to this sum. So we apply, I wrote equal, but this should actually be an inequality, but it's an inequality in the direction we need. So this is just Cauchy-Schwarz. D minus 1 on the second factor because you have D minus 1 factors in that tensor product. And then our Sobolev bound, together with some harmonic analysis, translates into this. So this first factor over here, the RT of mu j, is another L2 of mu j, so the D minus 1 goes up to D, times this factor, where the D minus 1 over 2 comes from the fact that that's the Sobolev bound we had. Okay, so we have these L2 norms of mu j, and you can estimate those using the energy integral and get this. So the upshot here is just that we have a geometric sum, and we can say when this is bounded. So the sum is finite when S is greater than the dimensional threshold I claimed, D minus 1 plus 1 over D. Okay, so that's the kind of the idea of the proof for the K equals D case. How do we reduce to the K equals D case? So for general K greater than or equal to D, we still have this same idea for the approximation. So it's now epsilon to the minus m because T is lives in an m dimensional space, and we're integrating over we're integrating d mu to the k of x over the region where the volume type of x is approximately equal to T. Okay, so that means when we take an L2 norm, I'm sorry. Yeah, sorry. So when we take an L2 norm, what we're doing is we're integrating d mu to the k of x, d mu to the k of y over the region where the volume types of x and y are approximately equal to each other. So what we said before is that, again, ignoring degenerate cases, if the volume types of two configurations are equal, you have a G in SL2, or sorry, in SLD that maps one to the other. So you can prove approximate versions of this as well, and that lets you write this integral. This lets you do like a kind of a change of variables where we replace the integral in x and y with an integral in x and g, where dg is a Haar measure on SLD. So this becomes. We do a little Wood-Paley decomposition again. So this becomes the integral of mu j of gx1 through gxk. So you can think of this as replacing the d mu to the k of y, right? So you can think y equals gx, and then we do the little Wood-Paley decomposition and write it this way. Okay, so we're integrating mu j of gxi, the product over all the i's, and then we're integrating it against d mu to the k of x and the Haar measure dg. Okay, so what do we do here? Well, our goal is to reduce to the k equals d case. So we just apply L infinity bounds to a bunch of the to k minus d of the terms. And what we get is this factor out, that should just be j, sorry, not jd. So there's 2 to the j times d minus s, that's the L infinity bound we have, and then times k minus d, because that's how many factors we've estimated away. And what we're left with is an integral that's exactly the one we were dealing with in the k equals d case. So again, you then convert back out of the dg back to the d, mu to the d of y, and you have the same integral we just analyzed. You can write it in terms of these generalized radon transforms again, and apply the same ideas. You again get a sum of 2 to some power, and you work out when that power is negative so that the sum converges. And you find that the sum converges when S is greater than the threshold I claimed, d minus 1 over 2k minus d. Okay, So so the next thing I want to give is an example showing how sharp this is. So maybe calling this a sharpness example is a bit of a stretch because there's a pretty big gap between this and what I claimed. For any s less than d minus that fraction, there exists compact E O, that should be an RD, E and RD with dimension s, such that the set of volume types has measure 0. Okay, so what this does tell us is that as k goes to infinity, this threshold here goes to d. So you can't hope for any theorem of any threshold independent of k, any non-trivial threshold independent of k. Whatever the true kind of sharp threshold is, it has to tend to d. Okay, so the idea here is a kind of standard, a version of a standard example of an approximate dimension S set. So what you can approximate a dimension S set by taking a lattice in the unit cube with spacing 1 over q and thicken each point by q to the minus d over s. So you take a ball around each point in this lattice of radius q to the minus d over, sorry, minus s over d. Sorry. So for large Q, you can think of this as an approximate version of a dimension S set. And to exploit the kind of symmetry, the rotational symmetry that volume has, we map the square lattice to a spherical lattice. So graphically, this is all we're doing. So like this is our classic example of an approximate S-dimensional set. I guess to be one step more rigorous, right? If you take an intersection of lots of steps like this, as Q grows very, very fast, the intersection over the sequence of Qs has dimension S. So we take this grid and we map it to a spherical grid. I've drawn the examples in 2 dimensions. And the point here is that any volume you can get by choosing some of these points, you could always get an equivalent volume type with the restriction that the first point has to lie on, say, the first axis, right? Whatever configuration you have, you can always rotate it so that one of the points is on the first axis and preserve volumes. So that means if you look at just the grid before we inflate the points, you have Q choices for that first point, and then there's K minus 1 points left, and you have D choices for each of them. So you have at most this many volume types. And when you thicken it, right, so around each of those volume types, which is, right, so this is how many lattice volume types we had, and around each one, you have you've thickened it by Q to the minus D over S, and this is in the dimension of the space of volume types is this. So this is this total quantity is the volume type, or the measure of the set of volume types for that thickened set, the approximation. So as Q goes to infinity, this will tend to 0 if S is where I claimed it was, and that means that the resulting set would have measure 0 volume types. Let's see. I think I had a couple more slides, but I should probably wrap it up here. So this is a nice stopping point. This is the proof of that theorem. So I'll end here.
Okay, thank you very much for nice talk. Please, questions or comments? Actually, I have a small question. In the theorems, as a condition for the dimension E, is it a necessary condition or sufficient conditions?
For which theorem? For the
just like in few theorems, it was conditioned like here, for example, for dimension E, like larger than D. Is it necessary condition or sufficient condition?
what is the condition on the dimension?
If the dimension E larger than D minus.
Yeah, so it's sufficient. I'm not claiming that this is sharp. You might be able to get a result for you might be able to get a better threshold also. Right? So like in the original Falconer problem, right, you had like D plus 1 over 2, and the conjectured threshold is D over 2. We know that D over 2 is sharp, but we don't know if we don't know how close you can get to that. So these are all I don't think for like the quote unquote sharpness theorem I gave shows that you can't, there's a limit to how much you can improve that threshold, but I'm certainly not claiming that that the threshold I proved was sharp. So yeah, it's not necessary, at least as far as I know.
Okay, thank you. Please, some other questions, comments?
Yeah. So I might have missed it, but in these theorems, is there a conjecture analogous to the Falconer conjecture for these k point configurations?
Yeah, that's a good question. I'm not sure what a good conjecture would be. No.
Okay.
Yeah, I guess the best example, or the best lower example I have is the one I gave, which is looking at this. It's like in the k equals d case, this is pretty bad. So yeah.
Is there a conjecture at least what happens with the triangles, or even with the triangles? It's not completely clear.
Triangle. So for yeah, I'm not sure.
Yeah, that's fine. Yeah, it actually makes it even more interesting, even if the conjectures are not clear. Okay. Thank you.
Please, some other questions, comments? Okay, maybe if it's not the case, let us thank the speaker again. Thank you very much for a nice talk.